Welcome students to this unique initiative of digital practicals for class 12 in physics. I am Jay Roy, PGP Physics, Mother's Public School. Today we will be discussing another experiment based on potentiometer. So the aim of the experiment is to compare the EMF of two given primary cells by using a device called potentiometer. And of course, the apparatus required for the experiment, we have potentiometer, we have two primary cells, one is a Leclanché cell, the other is called a Daniell cell. Then we need an ammeter, a voltmeter of course suitable ranges. We need a galvanometer, we need a battery eliminator, which is going to act like our power source. Then we need a rheostat, a variable resistor, a resistance box, one-way key, another two-way key, a jockey and some connecting wires, and of course some sandpaper to ensure that we have clean connections of the wires. Okay, but before we start, let us first understand what exactly is a potentiometer. We have learned about meter gauge. Meter gauge is a device which can help us determine values of moderate values of resistances which are not very small or very large. But potentiometer is a very sensitive device. It can help us determine very small resistances. And apart from determining very small resistances, it can also be used for comparing the EMF of cells. And we are going to use the potentiometer later to determine the internal resistance of a cell. So before we proceed, we need to understand a few facts about cell, EMF, terminal potential difference and internal resistance. So a quick run through will certainly help us understand how to conduct the experiment. So if you take a cell and suppose there is an external resistance R connected. So these are the two terminals of the cell. We have an external resistor and we have a key. Suppose the key is open, that means the circuit is open, the key is not closed. And then if you have some kind of device to measure the potential difference between the terminals of the cell, the ends of the two sides, two terminals, then you will get some reading. That reading is called EMF of the cell. So EMF is the potential difference between the terminals of a cell when the circuit is open or when no current is flowing through the cell. And it is dependent on the nature of the electrolyte of the cell. But the moment you close the key, a current will start to flow. Current starts to flow in the circuit. And you will see that there is a drop in the reading. So this device is going to measure potential difference. So you see the moment you close the key and the current starts to flow, this reading will be less than what you had got previously. And this value of V is called terminal potential difference. So let me know, E is EMF of cell, V is terminal potential difference. Now why is this V less than E? This is because now the current is flowing through the cell, and because the cell is made of electrodes, electrolytes which are going to have their own resistance, so we can think of an extra resistance apart from the external resistance that we have connected to come into the circuit. That thing is called your internal resistance, small r. So it is the resistance offered by the electrodes and the electrolyte to the current. So how much is the drop of potential when the current is flowing through the cell? Well, across this end you are going to expect a small drop in potential which is I into R. Okay, so this V is actually less than E by what factor? IR. And IR is called your lost potential. So internal resistance is a very small resistance that the electrodes and the electrolytes offer. and over a period of time, when you use the cell more and more, the internal resistance will go on increasing. As a result, the effective potential provided by the cell to the device connected will go on decreasing. Okay. So now our purpose is to measure this internal resistance later, which we will do, and of course compare the EMF of the two cells. So before we proceed, let us first find out how much is this internal resistance, which we can use later. So if you look at the circuit, the total current drawn from the cell is given by R plus small r, because capital R and small r are connected in series. So the overall resistance of the circuit is R plus R. Total EMF of the circuit is E. So the current drawn from the cell is E by R plus R. And when you plug in this value here, so terminal potential difference will be E minus E by R plus R into small r. And doing simple math, you can see V can be written as ER plus ER minus ER by R plus R. This gets cancelled, or V capital R plus V small r is ER, or small r is E minus V by V into capital R. So please remember this, we are going to use this formula later. So R happens to be the internal resistance of the cell. So it is relevant for all of us to go through the basic theory behind the experiment. Is it clear to us? Okay. So small r is E minus V by V into R. So next thing that we are going to understand is what exactly is the potentiometer. I have said that you can use meter bridge to determine resistance, but when it comes to measurement of very small resistances or very large resistances, meter bridge has its own drawbacks or limitations. So that is where potentiometer comes in. Here potentiometer uses length as a parameter to measure potential. So that is why the name, we are going to measure potential by using length. So hence the name potentiometer. So every device that we use has some principle behind it. So first let us understand what is the principle behind the potentiometer. Now we all know Ohm's law. Current is proportional to potential. If you go on increasing the potential difference across a conductor, the current in it will go on increasing. And mathematically, the macroscopic form of Ohm's law is given by V is equal to I into R, where I is the current, R is the resistance. And we also know that resistance is rho into L by A, where rho is called the specific resistance or resistivity, L is called the length, A is the area of the cross section of the wire. Now imagine that, so if I plug in the value of R here, it becomes I rho by A into L. So if we can keep the current flowing in the conductor constant, resistivity remains constant by keeping the temperature and the nature of the material constant, and keeping the area of the cross section of the wire constant. So I keep this entire factor constant. Then can I not say that V will be proportional to L? Yes. So if I keep I rho by A constant, so that will imply the potential drop across the length of the conductor will be proportional to the length of the conductor, provided current, resistivity and area of cross section remains constant. And that exactly is the principle behind the potentiometer. So I can imagine a constant of proportionality K. K is called the potential gradient, and it is given by V by L. So whenever a physical quantity changes with distance, we use the term gradient. So potential changes with length, so that is why K is called potential gradient. So we are going to use length as a parameter to measure potential. Okay, so V, so let me explain it. Suppose there is a wire and I take two different points, point A and point B. Suppose this length is LA and this length is LB. And suppose this is at a higher end, this is at a lower potential. So current flows like this. So there is a potential drop as you go from left to right, from A to B. So if I ask you what is the potential drop between A and O, that will be proportional to LA. If I ask you what is the potential drop between point B and point O, that will be proportional to LB. That is exactly what it is. And if you want to find out the potential drop between A and B, that will be proportional to LB minus LB. Is that clear? So that is what it means, that potential difference or potential drop is proportional to length of the conductor. Now, how to use potentiometer to determine the ratio of the EMF of two primary cells? That is the first thing that we will discuss, and later another experiment deals with determination of the internal resistance. So first let us understand what exactly is a potentiometer made of. Now going back to this circuit that is already presented here, I'll draw a relevant circuit here, but you can see this is the circuit diagram that is relevant for our setup, experimental setup for determining the ratio of the EMF of two cells, E1 and E2. I draw the same circuit but a much simpler looking circuit for all our understanding. So let us draw the circuit. It's just the same circuit but a simpler looking circuit. So you can see I have drawn another circuit. It is essentially the same circuit, but you can see that I have the cell E here, which is the cell here. This is called the driver cell, or sometimes called the auxiliary cell. Why it is called driver cell? Because it drives current into the circuit. And then there is a rheostat. All of us know rheostat is a variable resistor. If you slide that the contact moves, the resistance increases or decreases. So this rheostat is there to control the current that is flowing into the circuit. So if you increase the resistance, lower current will be drawn from the driver cell. And if you decrease the rheostat, then more current will be drawn from the driver cell. Then you have an ammeter to measure how much current you are sending into the circuit. And then there is a key to stop or start the current that is going to flow into the circuit. In case of meter bridge, you have seen that there is one single wire of 100 centimeter length or 1 meter length. But in a potentiometer, you will say multiple wires. You can have 5 wires, you can have 6 wires. Later, you will be actually looking at the setup and getting the experiment. But in potentiometer, you will see many wires. In fact, there are 5 to 6 wires, each of 100 meter length. It is one single wire, but it is connected. As you can see, one wire. So 1, 2, 3, 4. So even though the entire wire is 400 centimeter, it is divided into 400 centimeter wires, but connected by this copper strips so that the continuity is maintained. So what I have done is that instead of drawing this long wire, I have just drawn one single wire without affecting the technicality. Now what we will do is, we will understand how this circuit works. You can see that there is a gap here in the circuit. There is a galvanometer and there is a jockey. Okay. So our requirement is to determine the ratio of EMF of two cells. So let us take two cells. In your experiment, you will be dealing with two cells. One is a Leclanche cell, the other is a Daniell cell. Those are wet cells where the electrolyte is in the liquid form. Okay. So later that will be explained in greater detail. So I want to compare the EMF. So what I will do is, I will connect the two cells like this. And here I am assuming that they are of negligible internal resistance. So how do we proceed? Just a quick run through of how we got into the working formula. So what we will do is, first we will close the key. So step 1, we close key. And then we slide the jockey on the wire. This wire is made of constantan or manganese, which is a standard resistor wire. So you slide the jockey on the wire to obtain what? The balance point or the null point or the null deflection point in the galvanometer. So you try to find a point where the galvanometer is not showing any current flowing through it. So suppose this point is A and this point is J1, where you have obtained the balance point. So close K and obtain balance point at J1. So AJ1 is suppose L1. Suppose this distance is L1. Now I know by principle of potentiometer that the potential drop across this length will be some constant K into L1. Let that be equation 1. Agree? Now look at this circuit. So once you close K1, yes, close K and of course join into E1. So this two-way key is now connected to E1. So now after that only current will flow. So then you start the jockey and get the balance point. So VAJ1 is created. Now if you look at the circuit, A, J1, E1 back to A. If you look at this circuit, this is a complete loop. So if you apply Kirchhoff's rules, the total potential drop in that sum of all potential drops should be equal to E1. So by Kirchhoff's rules, potential drop, what is the potential drop? Only potential drop is VAJ1. So that potential drop, because there is no current flowing through this end, so there is no potential drop here. So this potential drop must be equal to the net EMF in the circuit. So that is equal to E1. Let this be equation. So from here, what do I get? E1. So from 1 and 2, we get E1 is equal to KL1. Let this be equation 3. We have not determined E1, we have found out that E1 is equal to K into L1. Now the second step is connect this key to cell E2. So when you connect it to cell E2, this is not part of the circuit anymore. Now E2 becomes a part of the circuit. So when you connect it to E2, you will see that there will be some current flowing through the galvanometer because now the balance point has been disturbed. So now you try to slide the jockey and try to find out the balance point later. So close, I'll call this K1 and K2. So here close K2 and obtain balance point at J2. Suppose now the balance point is obtained here. assuming that this length is now L2. So L1 was the previous balancing length, L2 is the new balancing length. So close K2 and obtain balance point at J2, and AJ2 is L2. But by principle of potentiometer, we know VAJ2 is equal to K into L2. Let this be equation 4. So potential drop from point A to J2 should be proportional to length L2. That is what I have written. K being the constant of potential. Now what you will do is apply the same Kirchhoff's loop but to the new loop. The new loop being A, J2, galvanometer through E2 back to A. So when you go through this, you will realize that only EMF in the circuit is E2 and only potential drop that is taking place is KL2 or VAJ2. So by Kirchhoff's rules again, voltage law, what's the loop law? VAJ2 is equal to E2. So now what do I get? So from 5 and from 3, I get E1 by E2. Oh, sorry, this is of course KL2. So it is KL1 by KL2, or E1 by E2 is simply L1 by E2. So the ratio of the EMFs is nothing but the ratio of the balancing lengths when the two cells are connected in succession. 1. And then you will have to conduct the experiment. The proper experiment will require a little bit of effort, and you have to be very, very careful. Certain things that will be explained to you, that the driver cell should be a cell of large EMF and balanced EMF and constant EMF. And the cells E1 and E2 that you are connecting should have EMF less than E. It should, remember, E1 or E2 cannot have balancing length greater than E. Otherwise, you will never get a balance. Because the maximum potential drop from point A to point C is E. It cannot be greater than E. So that is where you have to be very, very careful to obtain the balancing length. Now you have to conduct the experiment. You have to find out that there is a milliammeter reading. This is a milliammeter, and then you conduct the experiment with the first cell. The first cell will be a Leclanché cell. You find out the balancing lengths with proper resistances. Then you find out the balancing lengths for the Daniell cell, and then take the ratio. So this is basically the experiment. Ma'am will be explaining the details. Will be demonstrating how to conduct the experiment. Over to you. Thank you.
Welcome back to this online classes of physics lecture. This is continuation of experiment 4. It is to compare the EMF of both the cells. Here, two cells are taken. One is Leclanché cell, the other one is Daniell cell. In case of Leclanché cell, ammonium chloride solution is taken as electrolyte. Zinc chloride, negative electrode, and carbon positive. This is Leclanché cell. And it is Daniell cell. Copper itself is taken as positive electrode, zinc chloride, negative electrode. Inside copper vessel, copper sulfate solution is there, and within the course of dilute sulfuric acid is there. We are going to compare both the cells, that is Leclanché cell and Daniell cell, using potentiometer. Now, come to circuit arrangement. As it is shown in the diagram, the zero end of the potentiometer is connected to positive terminal of the battery emitter. Then battery emitter, key, milliammeter, rheostat, all are connected in series. The other end of the rheostat is connected to 1000 centimeters. That is the end of the potentiometer. This is the zero end of the potentiometer, which is connected to all positives. Battery emitter positive, Leclanché cell positive, Daniell cell positive. All three positives are connected to zero end of the potentiometer. Now, connected to jockey. The purpose of checking two-way key is as we are going to compare both the cells, that is Wickland cell and Daniell cell, we have to connect one cell at a time. So when Wickland cell is in connection, then we put the key between this point, midpoint and the other orbital. Put the key here, now Wickland cell come to connection. But as the key is not there, here this contact is open, so Daniell cell is not in the circuit. Similarly, when we take the Daniell cell into a connection, we will put the key here in the gap, so that Daniell cell will come into circuit, but Wickland cell is open. Then we will find the balancing length for both the cases and we will find the ratio. So first of all, let us start with the Wickland cell. Here we have taken a high resistance box. With the resistance, the galvanometer shows A1 deflection. So to save the galvanometer, to reduce the deflection, in between we take deflection with high resistance. That's why we are taking a high resistance box. How we say a high resistance, at least 2000 ohm is used basically. Now, to start with, once the connection is done, the connection should be made and untied, and we will check whether the connection is correct or not. To start with, we will check at the 0 end, cross the jockey slightly at the beginning, it shows right and deflection in the galvanometer, then it does at the other end, it shows left side deflection. If it shows both end deflection, then the connection is correct. Suppose I will do something wrong here. Suppose I will remove this key and touch. Then it will show one side deflection. That is here, this side. You will see it shows right side deflection. Here also at the other end also it shows right side deflection. That is, when something is wrong, it will show you, galvanometer will show you one end deflection. Or if the EMF of the driving cell is less than these individual cells, that is Wickland cell or Daniell cell also, it will show you one end deflection. So by checking this deflection, you will know whether the connection is correct or not, and accordingly you will take steps. Now let me put the key where the door. Now to start with Wickland cell is in connection, we have to find out the balancing length. First, we have to fill up the observation table. Earlier, you will note down what is the EMF of the battery elevator. Always we set the battery elevator at 2 volt. That is enough. So, EMF of battery elevator 2 volt. Now, we can roughly, and to verify this experiment, we can roughly find out the terminal, the EMF of both the cells, Wickland cell and Daniell cell, using a voltmeter. Switch it off, no current is flowing. Now, as no current is flowing, we pass the positive of the voltmeter to the positive of the cell and negative of the positive of the voltmeter connected to positive of the cell and the negative terminal of the voltmeter to the negative of the cell. It shows around 1.45 volt. So, EMF Wickland cell now at this situation, at this concentration and at this distance between two electrodes, the EMF is now 1.45 volt. EMF varies according to the concentration of the distance between electrodes, the EMF may vary. Now let us check the EMF of Daniell cell. Connect positive of voltmeter to positive of the cell. Negative to negative, it shows around around 1.05 volt. So EMF of Daniell cell shows around 1.05 volt and Wickland cell shows around 1.45 volt. So we see using the potentiometer, what are we getting? That is 1/2 should be almost nearly equal to the ratio of 1.45 is to 1.0. 605. Okay. And now come to current cell. First, serial number you will take 6 to 7 observations for this experiment. Then millimeter reading. The current flowing now set 20 milliampere. The range of the milliampere is here 500 milliampere. This term is 10 milliampere. Current flowing is now 20 milliampere. So current flowing in the milliampere should be mentioned 20 milliampere. Now this cell is in connection. Here 2000 ohm we have to take the balancing point. So both touching the first wire, it shows right reflection, and the second wire right reflection, third right, fourth again right. Immediately you remove, don't put contact with the wire for a long time, otherwise the galvanometer will be damaged. Then check on fifth wire, right reflection, sixth right, seventh right, eighth. Now on the 8th wire it shows you left reflection. That means the non reflection lies somewhere between 7th and 8th wire. So you will go on checking along the 7th wire, then we will come to 8th wire to find the non reflection point. So we will go on checking along the 7th wire. Then we will come to 8th wire. Just touch it gently, don't place it hard so that the resistance per unit length will vary. Now, this is the non-reflection point. You may use a small scale. You may use a small scale to take the reading. Now, at this point, we are getting the balancing length, that is the galvanometer source reflection. So, at this point, so what is the balancing length now? On the 8th wire, balancing length is coming. So 700 complete plus extra. So you will use this scale. 700 is here on the 8th wire. So starting from 0 it is 62. So 762 is the balancing length L1 without 2000 ohm. Now second one, balancing length with 2000 ohm. So here from the resistance curve, you will take out 2000 ohm. So as we are applying high resistance, now the reflection will be little reduced. But balancing length almost comes at the same point. So check around the same point, it goes right on the 7. Again you come to it where zero now. It is around 787. So then 787 and the mean value. We got mean L1 for frequency. Now we will find balancing length for Daniell cell. So if this we put it here, connect between the Daniell cell and the galvanometer, replace the 2000 ohm, and again you will check. In the first pair, right reflection, second, right third, right fourth, fifth, sixth. It is on 0. Galvanometer shows 0 reflection. On the 6th pair, there will be 0 reflection. So 500 complete there. Then after 500, on the 6th pair will be something. So you will use this scale. It starts from 0 from here then, and it is now say 558 centimeters. That is without 2000. So here under Daniell cell you will write without 2000 now 550. Now with 2000. Again remove 2000 ohm. Your balancing length again will come on the 6th wire most probably. So 500 here, yes, got it here now. It is around 562.5. No doubt you will find the mean. So you got mean. At the last column, E1 by 2 is equal to mean L1 by mean L2. Here you will find E1 by 1 observation complete. 1 observation complete, then you vary the rheostat. Current will vary a little. Note down the current. Then replace the key. Again bring the liquid cell to pixel. On the 7th where it shows right pixel, on the 8th where it shows left pixel. That means between 7th and 8th again 0 pixel. So it is showing on 0 pixel. So you got 734.5. Next again 3000 kind of color sequence and one here. You got mean and replace this key, bring your Daniel connection. Similar process to be followed to find mean and 2. Go 2000 again 8,2000 and 2 times you will find the mean, that will give you mean and 2. Again find L1 by L2, that is the ratio between the both the cells. So take 6 observations and you will find the ratio between both the cells. Here, what are the precautions to be taken? First thing, the connection should be clean and tight. The resistance box should be tightly closed, and the jockey should not be crossed hard under, where when you are not taking observation it should be switched off, and the EMF of learning cell should be always more than that of the literature and learning cell. These are the precautions to be taken. That's all. This experiment, and again we will come to next experiment. Each experiment has theory will be explained by sir.